Hi everyone, today we are going to discuss about MergeSort. So MergeSort is an efficient sorting algorithm. So it has time complexity of n log n, whereas space complexity also revolves around the same order of n. And so usually it is a divide and conquer algorithm. So let me explain what is divide and conquer here. So what is divide? Divide the unsorted list into n sublists, each containing one element. So that means you are dividing this entire list into two equal parts at the first step, and later you are dividing this sublist into two equal parts, and later you are dividing this sublist into two different parts until the size of the array is equals to 1, because when the size of the array is equals to 1 you cannot further divide this array. Understand? So like that is the divide one. And what is conquer? Conquer is nothing but how you write some method to iterate through these splitted arrays. I think you understood about that. So you had splitted these arrays 5, 2, 4, 7, 1, 3, 2, 6. But what you have to do with that? So splitting is not your goal, right? You have to do something such that the array will get sorted. So now the conquer will do repeatedly merge sublist to produce a new sorted sublist until there is only one sublist remaining. This will be the sorted list. So this is a conquer method here. So the MergeSort is divide and conquer method. So let us see how this happens. So first you will take this array, you will consider your low, you will consider your high, and you will divide it by 2, low plus high by 2, and you will get your mid. You will have your one array from low to mid and another array from mid plus 1 to high. So we'll do iteratively same process for recursively for same arrays. For this we'll apply the same, it will divide into two parts, and we'll apply the same 5 2, 4 7, 4 7, 1 3, 1 3, 2 6, 2 6, and we'll do this we'll divide these arrays until the size of the array is 1. So up to here divide method is completed. Now we have to do conquer. That means we have to merge the sublist again such that it is sorted. So now let us consider this example. So 5 2 is split into 5 and 2, but when you are combining these two, we should make sure that these two form a sorted sublist array. So that means you are dividing one big problem into multiple small sub problems to solve that, so that we can easily sort them. So now when 5 2 is divided into 5 2, now you will check. Let's consider this as left array, and let's consider this as right array. So now you will keep a pointer to your left and you will keep a pointer to your right, and now you will check whether left is less than right or not. If it is less, then you will include this element, but in our case the right is lesser, right? So we'll include 2 and we'll increment the pointer of the right variable right plus plus, and we'll do the same with this side. So at now the array is completed on the right side. Now we'll iterate on the left side. So what is the leftover element on the left side? It is 5. So 2 5. In the same way we'll combine 4 7, 1 3 and 2 6. We'll form this array 2 5 and 4 7. So now the left will point to 2 and the right will point to 4. So now you'll check whether left is less than right or not. Yes, it is less. So we'll include 2. Now we'll increment the left pointer. Now the left points to 5 and the right points to 4. Now we'll check whether left is less than or right. So no, right? So we'll include 4 here. Now we have included 4, and we'll increment the right pointer to 7. Now the left points to 5, the right points to 7, and we'll check whether we'll compare these two. So now 5 is lesser, so we'll place 5 here, and later we'll place 7 here, and the same with 1 3 and 2 6 array. It will come out to be 1 2 3 6, and now we'll apply the same on these two. So it will become 1 2 2 3 4 5 6 7. So this is a sorted array. So in this way the MergeSort algorithm works. So basically we have two functions. One is divide, one is merge. So what divide does, it divides the single subarray into multiple subarrays of size 1. So that is the theme of divide. So what does merge do? Merge, what it does is it combines the array in a way that the array is sorted. Okay, so now let's discuss about the time complexity. So MergeSort has a time complexity of order of n log n, like for all the cases, for best, for average and worst. So the divide step obviously takes order of n log n time, as we are dividing array into two halves. So I think you watched my lecture regarding the binary search, which include the binary search also have a search time of log n. Why? Because every time we are dividing the array into half. So that is log n. And merge step, each this step takes order of n time for each level of recursion, as we need to merge all the elements at each level. So what is login here? Login is nothing but the height of the tree we formed here. So you can use your logic here, 8, 2. So the log 8, what it will be 3. So the height 1, 2, 3. So the height is 3. So in the way, so 3 into n, each step takes merging like n, 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 n. So we are taking order of n into log n. So that is order of n log n. Since divide step and merge steps are performed log n times, the overall time complexity will be order of n log n, obviously. So next, what is the space complexity? At each movement, we are storing our left array, we are storing our right array. At each step, we are using order of n space. That means we are using an array. So the auxiliary space of order of n is used. And what are the advantages of merge sort? So first of all, it's a stable sort. So that means in all the cases you have the same time complexity, like order of n log n. That means that consistent performance. So what are the disadvantages? So the main disadvantages of merge sort are, so like it will consume some space. It is consuming an order of n space, right? So that is the main issue of merge sort. And when we compare the merge sort and the insertion sort, so merge sort takes the time complexity of n log n for every size of the array. But whereas for insertion sort, if we look at carefully, if the array is sorted, the best time complexity is order of n. And the insertion sort is also works better for the smaller arrays. So we will see in future lectures how we can improve the merge sort time complexity by using the insertion sort. So we'll use those two algorithms in order to improve the efficiency of merge sort. So let us look at that particular algorithm in other class. So let us discuss the code of merge sort here. So basically, let's start with the merge sort. So what is our theme? If the length is probably equals to 1, we need to stop our like division, right? So what we can do is, if low is less than high, then only we'll try to make a recursive call. So first of all, let us consider what is our mid. So first of all, we need to choose our mid element. So you can choose a sparse int. You can have low plus high by 2, which will give us a mid element. And now you will call the merge sort function. Like I said, your initial merge sort will be from low to mid, right? So you can call from low to mid, and later the call will be from mid plus 1 to high. And now what you will do is, like after completion of if you divide an array at a size of 1, so when you come till the size of 1, you have to do the merge sort. And after completion of this, what we need to do, we need to merge all this. So we can write as merge, and now you'll have your array, and you'll have your low, and you'll have your mid, and you'll have your high. So I hope you understand up to this point. Like basically what we are doing is, like we are recursively making the calls low, mid, the left side of this is the left part of the array, and this is the right part of the array. And we are basically merging these two parts under the condition that the final array is sorted, right? So I think you understood this one. The main concept of merge is to give us a sorted array when we provide two arrays to it, right? So let's create a left array. And a right array, which are initially empty. So now let's fill this with elements. So this will be from low to I less than or equals to, and the right plus plus, right? And you'll push these elements into our left array of 5. And in similar way, we'll fill the right array also, like that from I is equals to mid plus 1 to I less than or equals to high to I plus plus. And now you'll have your right array dot push to array of 5. And your two sides of the array are completed. So now what is our main task? To create a resultant sorted array. So let us make it as some resultant array, And now let us have two pointers, like basically they are the indices pointed to the left array and the right array. So let us have left index which is pointing to 0 and the right index which is also pointing to 0. So now while your left index is less than your left array dot length, right, and then your right index is less than your right array dot length. So this is your condition to run. So now what we can do is, if our left array of left index is less than right array of our right index, then that means our left index element is lesser when compared to the right index element. So simply we can push this element into our resultant array and we'll increment this index, or else what we can do, else result dot push our right array element into our resultant array, and I'll simply have this. But in some conditions, like whenever you can have the condition like whenever your left array is completed, there are still elements left in your right index element, like we have seen in our previous case when we are discussing about MergeSort. So to avoid that issue, we can simply place that left index is less than left array dot length will still traverse until this is completed. So result dot push your left array of left index plus plus. That's it, right? And you'll also do the same. What if your left array is entirely traversed, but you have still elements left in the right array? So we'll do the same with the right array also. Right array dot length, and your result dot push your right array of right index plus plus. And now the main thing is you have created the resultant array. So you have your resultant array stored in your resultant array. So now we have to place all these elements in the right position. So how you can place? So let us consider index k which points to 0. So that means it points to the start of the resultant index. So now we have to place this element in the place of array. So we can place let I is equals to low and I less than or equals to high and I plus plus. We will place array of I is equals to result element of k and we'll simply increment the counter. So I think you understood this method which I used. So basically what I am doing is like I am traversing until whether the left index crosses our bounds of left array or right index bounds exceeds the bound of the right array, and we'll traverse this. What if the right array is completed but the left array is still left out? So this will handle that condition, and vice versa. So now we have our resultant sorted list in our resultant array, but now our goal is to place these elements at the right place, that means our array. So what we can do is we can simply declare a variable like k which points to the start of the resultant array, and we'll traverse from, like we have to place all these elements in from low to high, right? So we'll traverse from I is equals to low to I less than or equals to high and I plus plus, and you will place these elements at resultant k plus plus. So now we can let me run this code such that you will understand whether it works or not. So let me start a new terminal here, and so let us run. So node MergeSort.js. So I think you can see that the array is sorted, right? 1, 2, 2 and 3 and 4, 5, 6, 7. So 1, 2, 2, yes, 3, 4, 5, 6, 7. So that's what the array we got here. So I think you understood the lecture about MergeSort. So I'll discuss in the next lecture that how we can improve the MergeSort time complexity, that means the best time complexity using insertion sort. I think next lecture will be more interesting. So let me discuss in that chapter regarding how we can combine insertion sort and MergeSort.